Hi everyone. Today we're going to discuss equations. Not how to solve a particular equation, but rather a more theoretical discussion about what equations are. So on the bottom of the screen here you have a sample equation. We are basically comparing two numbers. A number on the left, a number on the right, with an equal sign in between them. Basically, we're saying that these two numbers are equal. This is a statement saying that the number a plus 3 plus 9 plus b, it's an expression, of course, because there are many symbols here, but ultimately, once we know what a plus and b are, it's going to be a number. We're saying that that number is equal to the number x plus y plus 3. An equation is a statement, meaning that it could be either true or false. We might not know whether it's true or false, but it has to be one of those two things. If it's an example of a true equation is 1 plus 1 is equal to 2. An example of a false equation is 1 plus 1 equals 3. This is all fairly obvious, and it should be. 1 plus x is equal to 2 is an example of an equation that we don't know whether it's true or false. It could be true if x is equal to 1. It could be false if x is equal to anything but 1. But until we know what x is equal to, we just don't know whether it's true or false. Equality is an example of what's called a relation. A relation is a way of comparing mathematical objects such that the comparison is either true or false. There are many different forms of relations that we encounter even on a pretty basic mathematical level. For instance, inequalities are relations because they are ways of comparing mathematical objects, in this case numbers, such that the comparison is either true or false. 2 is greater than 3 is clearly false. 2 is less than 3, as we all know. 3 is greater than 2 returns a value of true. We can take any two numbers and use an inequality to compare them, and therefore, inequalities are relations. It doesn't have to always be number. For instance, congruence and similarity are also relations because we can compare any two geometric shapes and answer the question, are they congruent? Are they similar? So, for this one on the slide here, is this circle similar to the square? Well, by the very definition of similarity, the answer is no. And so this is a false statement. This circle over here is, in fact, similar to the smaller circle because that's what similarity means. They have to be the same shape. They could vary in size, but the basic shape has to be the same. And therefore, this is true. We can take any two shapes and make this comparison. So, therefore, they are relations. Now, what are we doing when we solve an equation? Solving an equation is the same as answering what values of the variable make the equation true. Those values are called solutions, and all the solutions are contained in what is called the solution set. So basically, instead of wondering, is the equation true or false, we answer what number values for the variable make it true. So here's a really simple example of solving an equation. We have the equation 1 plus x is equal to 2. And we ask, what values of the variable make the equation true? In this case, anyone will instantly know that x is equal to 1, and 1 plus 1 is equal to 2. So 1 is a solution to this equation. The way we write it below the x equals 1, though, is a little interesting. Instead of x equals 1, we say that x is an element of the solution set containing 1. At this point, it might not be clear why it's useful to write it like this. But as you will see, there are some benefits to considering x as a member of a set. It becomes more obvious when we have equations that have multiple solutions. So here's another equation. This time it's a quadratic equation. X plus 2 times x plus 5 is equal to 0. This is expressed as the product of two binomials. And again, we ask the question, what values of the variable make the equation true? And if you remember, we can make either one of these binomial factors into 0, then the entire expression becomes 0 and the equation becomes true. So the solutions are x can be equal to negative 2, or x can be equal to negative 5. Now, what's wrong or imprecise about the way we wrote it in the middle line over there? Well, Basically, anyone who's sane will know what we mean when we say x is equal to -2, comma, x is equal to -5. It means that x could be either one of them. But it's not exactly precise, because we're not saying that x is both of them, or whether x is one or the other. You know, it might be, in some context, we have two solutions, and they're different ways of saying the same thing. And maybe they're mutually exclusive, and maybe they're not. The set notation below is more precise, in that it says that x is one element from the set containing -2, -5. In other words, x is an element of the solution set containing -2 and -5. So in this case, it's slightly more elegant and definitely more precise to use the set notation to express the answer. So here's another equation. 0 times x is equal to 0. Again, we ask the question, what values of the variable make the equation true? And if you try some values, it quickly becomes clear that any number will work, because any number times 0 will equal 0. So therefore, x can be any real number, and it really becomes impossible to use x equals in our answer, because we'd have to write every single real number. We'd say x is equal to 1, x is equal to 2, x is equal to 1.99999, and there are an infinity of real numbers. So now is the first time that you really see how you can't always write x is equal to something. And we can't really say x is equal to any number, because there's no number called any number. Instead, set notation becomes very useful, because we say x belongs to a particular set of numbers. In this case, the real numbers. So x is an element of the solution set, which in this case is a big R called Blackboard Bold. That's the name of the font that the R is written in. And Blackboard Bold is usually used to write sets of particular mathematical objects, usually numbers. And in this case, the big R is the set of all real numbers. So in this case, it's the first time that we've really seen a case that we really have to use set notation, because otherwise we would have no way of writing all the solutions to x. We just say that x is a member of this particular club, this club of real numbers. So our last equation is 0x plus 1 is equal to 0. And a quick substitution will reveal that there are no values of x that make this equation true. No matter what x we pick, we multiply by 0, it'll become 0, we add 1, it'll become 1, 1 is not equal to 0, so there's no value of x that makes the equation true. And so we really can't write x is equal to anything, because x isn't equal to anything. Instead, we have to use the set notation to show that x is an element of the empty set. The solution set is empty. There is nothing in it. X is an element of this empty set. And that shows that there's no value of x that makes the equation true. There are no solutions. To say that x is equal to any particular number would be a lie. And if you wrote x is equal to no number, that's imprecise, because to say equals only works to compare two numbers. To say that x isn't a number isn't a comparison between two numbers. So it becomes essential that we use this notation to show that there are no solutions to this equation. Of course, on a test or on a given situation, you can just write the sentence, there are no solutions to this equation. But in notation, the way to do it is using the set notation below. X is an element of the empty set. So hopefully you've gotten something out of this. We showed that equality is an example of a relation, that all equations are statements that are either true or false, that solutions are values of the variable that make the equation true, and that it's useful to use set notation, especially in contexts that where the equation has more than one solution or has no solutions.